Now we can see about sampling theorem. Sampling theorem, it is only applicable for digital communication system. That is, it is an useful theorem that applies to digital communication system, and also it is used for signal processing. While we are going for the sampling, the signals can be converted into, that is, the analog signal is converted into digital signal, and it is converted in such a way that the sampling frequency must be twice greater than that of the 2 into FM, that is the highest frequency range. So only we can recover the signal at the original, that is receiver end. Here, while we are seeing on the signal, it's the continuous time signal. It is multiplied along with the train of impulse signal. Finally, we are getting the sampled version of the signal. This is shown by using this multiply. That is, the input signal is gone. That is, del T of t is the train of impulse signal. Finally, we are getting the discrete time signals. Here, while we are seeing from the above diagram, that is the continuous time signal, it is multiplied. That is, this sampled signal is multiplied with x of t and also the del of t, where del of t is the train of impulse signal, and this train of impulse signal is denoted by using this equation 1 by t summation of e power j n omega s into t. While we are substituting in the above equation, we are getting this equation. Finally, we are applying Fourier transform on both sides of this equation. While we are applying Fourier transform on both sides of this equation, by in the RHS side, while we are applying the standard formula, we are getting the values x of omega minus n into omega s, where omega s equal to 2 pi fs. We know that fs equal to 1 by t. Here we are applying the same concept in this in the above equation, and we know that fs equal to 1 by t. Therefore, this can be again modified as or rewritten as x of f equal to x of f into summation of x of f minus n into fs, where x of omega or f of omega, x of f is the spectrum of input signal, and x of omega or x of f is the spectrum of the sample signal. And here, while we are going for the sampling for the sampling theorem, here the continuous time signal x of t with the maximum frequency omega n, it is shown by using this spectrum, that is spectrum of x of. And here this is the spectrum, that is of t when omega s minus omega n is greater than omega n. That is, while we are satisfying this condition, there may be some gap in between the higher frequency components and also the lower frequency component. Therefore, there may be no overlapping occurs in this particular spectrum. And next one is omega s minus omega n equal to omega n. Here also there is no overlapping occurs. Therefore, there is no signal loss. Therefore, in this two conditions, the no overlapping doesn't occurs. Therefore, the signal can be reconstructed or recovered at the original end, at the receiver end. Here, while we are seeing this spectrum, that is omega s in this condition, omega s minus omega m less than omega n, in this condition there may be some overlapping occurs. Here, while we are due to this overlapping, there may be some signals are lost, and this is the effect called said to be aliasing effect. Therefore, due to this, some signals are lost in this particular area, and therefore the signal cannot be reconstructed at the original end. This is the condition already we have. Therefore, we must satisfy the condition that fs is greater than or equal to 2 into fm to avoid aliasing effect. And aliasing effect or fold over effect, it is defined in which says that the higher frequency component overlap with the lower frequency component. Therefore, this can be given as x of omega equal to 1 by 2 pi summation of x of omega minus omega s. It gets overlap, and the spectrum is the spectral overlap, and this is called the frequency folding effect. Occurrence of aliasing. Aliasing occurs if the signal is not band limited to a finite range and the signal sampling rate is too low, and also to avoid aliasing we should be strictly band limited, and also therefore should be greater than 2 into fm. Next one is Nyquist rate. We also know that Nyquist rate equal to 2 into fm, that is the minimum sampling rate at which the signal can be sampled and it will still be reconstructed from the sample without any distortion. Now we can, next one is data reconstruction or interpolation. In this and out in the receiver side, we are going to reconstruct the data or interpolate the data. That is, we know that the input signal is x of s t equal to x of t into this signal. Here, this is the sampled, this is a periodic train of impulse signal. While we are substituting t equal to n into t, we are getting this equation. The reconstructed rate is assumed to be linear and time invariant but having unit impulse h of t. And here, while we are reconstructing the signal can be given as y of t, which is equal to x of t into h of t. Therefore, we are just substituting this equation, that is integral of x of n into the summation of this h of t into del of t, and also For simplification, just we are changing the that is t equal to nt, and we also know that del of tau minus nt equal to 1 at tau equal to nt. Therefore, while we are substituting this equation, the final output will be y of t equal to summation of x of nt into x of minus nt. And next topic is the ideal reconstruction filter. The sampling signal is passed by ideal filter, and therefore and also the band limit width is greater than fm, and it is a passband amplitude frequency of t. Therefore, this filter can be given as this is the ideal response of the ideal filter. And here, while we are seeing this ideal filter, we know that h of t equal to integral minus fx by 2 to fs by 2 t into e power j omega e power minus j omega t. Here we are applying the values, that is we are just substituting that omega equal to pi into f, while we are simplifying, that is applying the integral and applying the limit. Finally, we are getting the signal function as this is the signal function. Therefore, y of t can be given as summation of x of nt into h of t minus t. Therefore, the above equation is in the form of sine function. Thank you.